So what we will do is we will deal with probability in some depth today. Okay. So what is probability? There are multiple definitions of probability. In fact, if you look at some classic textbooks, they would say that probability can be defined in multiple ways. They would say something called frequentist probability, which is what we saw yesterday. Proportions, that's frequentist probability. Then there is something called a heuristic probability. That's what economists usually do. They would say that the probability that there's going to be a recession in the next quarter is something. There is very little mathematics in it. It's heuristics. Okay. Then there are other theoretical probabilities and so on and so forth. And if you look at probability from a mathematician's point of view, they just treat it like some kind of an object with certain properties. Okay. What we are going to do is we are going to take the approach of frequentist probability. So this is also called empirical probability. So this is what we are going to do. But then we are going to implicitly assume that you can somehow magically generalize it to any kind of probability you are thinking of. But the properties of probability remain the same, irrespective of how you define it or use it. Okay. So before we talk about probability, there are a few things we need to have a clarity on. First, traditionally, when we talk about probability, we always hear a term called experiment. So what is an experiment? Experiment is basically the question that you ask. Actually, more than a question, the task at hand. That's a much better but vague definition of what an experiment is. For example, we might have in classic textbook cases of experiments are tossing a coin once or more than once, or tossing more than one coin at the same time, picking out a card from a shuffled deck of cards, okay, or observing the gender of a person crossing a particular segment on the road, right, or noting down the temperature at noon at a particular place. Okay, whatever be the task, some task we do, which could have more than one outcome. Okay, the task could result in more than one possibility. Okay, that's the kind of task we are interested in. That's called an experiment. Then we define what is called a sample space. The sample space is a set of all possible outcomes, and the set is denoted as capital S. Okay, like this, capital S. Sample space. So, for example, when a coin is tossed twice, what are all the possible outcomes? We could get head both times. We could get tails both times. Head on the first toss and tail on the second one, or tail on the first toss and head on the second one. So these are the only 4 possible outcomes. Okay. So if your experiment is to pick a card from a shuffled deck of 52 cards, then all possible outcomes are one of those 52 cards, right? If you pick 2 cards from that shuffled deck, then there are how many? 52 times 51 possibilities. 52 times 51 possibilities, right? First card, any one of the 52 you can pick, and then whatever is remaining, the second card you pick. There are so that's a very big sample space. Okay, so the sample space is essentially the set of all possible outcomes. If you are looking at the known temperature at a particular place, okay, then all possible outcomes, if you want to list all possible outcomes, can you guess how many members would be there?
Sir,
Known temperature.
You are asking any question, right?
Yes, I am asking a question.
What was that?
The question is, I'm measuring the known temperature at a particular place. What are all the possible outcomes of that measurement? Or how many? Now, if I get the set of all possible outcomes for the known temperature at a particular place on Earth, what will be the size? How many members can there be in that set of possibilities?
It's infinite, right? It's continuous random variable.
It is infinite, exactly, right? Because temperature is a numerical value, right? It's continuous. So it could be anything. So it's infinite. So some sample spaces are infinite. They have infinity of possibilities. Some sample spaces, like the toss of a coin or picking some number of cards from a shuffled deck of cards, even though they might be large, they are finite. No, two possibilities, two distinct categories. Please keep that in mind.
So just a question, sir. So when you say the temperature in a space, in a particular place, the number of outcomes could be infinite, right? So
yes,
you will define it by the decimals, let us say, right? To what extent you want to go, and also the known behavior of that place. So how can it be infinite?
Let us say I'm talking about Chennai Marina Beach. Okay, I do not know if you know about that place, but whatever it is, that's a place called Marina Beach in Chennai. Chennai is a city in South India, southern part of India. So there you measure, and historically we know that temperature at this place has never gone below 14 degrees Celsius, and it has never gone above 45 degrees Celsius.
Yes.
So it's going to lie between 14 and 45, whatever number we get. Now, if you allow for fractions, if you allow only integers, then there are only finite integers. 14, 15, 16 up to 45. So 45 minus 14, whatever that number is, plus 1. Right? So that will be 32 numbers. Now, if you allow decimal places, as you correctly pointed out, if our measuring instrument allows only one decimal place, then all you do is multiply this number by 10. Okay. If this allows two decimal places, multiply that number by 100. But theoretically, okay, since these are the temperature is a continuous, it can be any number. So theoretically, therefore, it is infinite, because between any two numbers, you have infinity of numbers with fractions. Okay, therefore, theoretically, it's infinite. But as you correctly pointed out, the measuring device sets the limit on whether it is infinite or if it is finite. You are absolutely correct.
Got it, sir. This is very helpful. Thank you.
So also I would imagine here that you could make the distinction between probability and possibility as well, right? Because the probability of it falling below 14 is low, but it's still possible to fall below 14.
Correct.
So therefore it would be infinite.
Well, it still can be finite depending upon your numbers, because nothing can go below minus 273.15 Celsius, right? That's the absolute zero. No, there is in physics, you have this absolute zero for a temperature,
Right.
and it's called 0 Kelvin, which is approximately minus 273 point some number, okay, some such small number. Therefore, even then, depending upon your instrument, if the instrument has only a few decimal places, then it is still finite. But possibility is infinite. Okay, so sample space is collection of all possible outcomes. Okay, yes, Prince, tell me please.
Coming back to that question of the temperature of a particular place. So, as you mentioned, that it is an infinite, right? Infinite possibilities are there. So, it means you are talking about the PDF probability density function, which lies
We'll
between
come to
the
that. We'll come to that.
infinity to infinity.
We'll come to that.
Okay. Okay.
Okay. Now, so when we talk about probability, experiment, the set of all possible outcomes is sample space. Then what we do is, this is more than this, defining a probability depends upon what is called an event. An event is usually mathematically defined as a subset of the sample space. But more than that, I'll make it, I like to say it as a simpler question. Okay, you ask a question about the sample space. You ask a question about the sample space and you get the answer. Okay, for example, in the set of tosses, in the sample space corresponding to 2 coin tosses, I ask a question. Okay, how I make a statement. It's not a question, I make a statement. I'm looking for at least one tail. At least one tail. When I say that, then the set becomes HT, TH, and TT. HH is not present there. It doesn't have a tail, therefore that's left out. So the event would be HT, TH, HH. Here it's at least one heads. One heads is HH, HT, TH. When you are talking about, let us say, drawing 2 cards from a deck of 52 shuffled cards. Let's say I'm looking at the event that there is a number 5. Okay, number 5. I have picked a number 5. Okay, that means it could be 5 of any of those 4 shapes, 4 kinds on the first one, coupled with 13 for the second. Okay, and 13 for the first, coupled with at least 5 for the 4 types. So 4 5s times 13, same thing for the second one, 2 times that many possibilities. Okay, so basically, as I'm saying, 5 of hearts with 2 of hearts, 3 of hearts, 4 of hearts, blah blah blah, and 2 of ace, 3 of ace, so on and so forth. No, like 2 of diamond, 3 of diamond, so on and so forth. Likewise, what is the other one? Clubs, right? Likewise, any of this with 5 of hearts in the second one. Oh, it's only started with 5 of hearts. Then it can be 5 of clubs, 5 of spade, 5 of diamonds. No, any of this. So we have some, but it's a subset of the original set. Okay, so event is some statement you make about the sample space, and you look at the set that fills the sample space, that fills the statement. Okay, say for example, you stand and observe. Okay, here is another example. Okay, you look at the grade sheets of transcripts of all the people in the class. Okay, so in their undergraduate degree, let's say we have the transcripts of all the people in the class today, and let's say we have the transcripts with us. Okay. The experiment I'm going to do is the courses. Okay. The courses people have taken. That's the experiment. So what would happen? It would contain the courses taken by the first student, second student, third student, all of them put together. That would be the sample space. Okay. Then I would ask a subset. Okay, I would look at the courses and say courses that had a lab component. Okay, courses that had a lab component. Not every course might have had lab component. Some of them might have had lab components, right? So a small subset, and that's what we are looking at. That's called event. So event, please do not confuse the word event in probability with the English word event. In fact, people usually say event happening, when talking about probability. Please don't have that in the mind. Event is a subset of the sample space. We ask a question, and the answer to that question is a subset of the sample space, and that subset is an event. Okay, so experiment, sample space, event. Now comes probability. Probability is defined as a number of possible outcomes for the event. Therefore, we define probability for an event, not probability for something. Probability we always define for an event. Probability for an event is number of possible outcomes for the event divided by number of all possible outcomes. That is, this is the size of the sample space. The denominator is the size of the sample space. Numerator is the size of the event. So it's a fraction, proportion. This is exactly what we saw yesterday when we talked about that probability distribution. Okay, but when you think about this kind of definition fails when you have the sample space to be containing of continuous numbers. Known temperature, for example. If you have continuous numbers, then this kind of probability definition fails. Okay, we will assume that we will not get into that kind of situation, so we will just talk about this like this. What happens when we talk about continuous values? Then the definition of probability changes a little bit. We will talk about that as we move along. Okay, right now let's think about the discrete case and assume that and understand that probability is defined for the event, and it is nothing but the ratio of the size of the event divided by the size of the sample space. Okay, that's what it is. Now,
sir, where does is sample space in this case equal to the population also? Can you talk about that?
No. That's an unfortunate. Confusion of the word sample space here and sample there.
Okay.
Sample and population, but it's not that way. We'll come to that.
Okay.
Just hold on for a minute. Okay, sample and population are very different. Okay, the sample space is dependent only upon the experiment you are doing.
Got it, sir. Thank you.
Okay, I apologize for this bad animation. We'll see what it is shortly. Okay, yeah, it is. We define some very special events. Okay, one event is called a null event. Null event is a set of all impossible outcomes. Okay, I toss a coin 2 times and I expect 3 heads, at least 3 heads. Okay, that's not possible. Okay, that's a null event. Okay, when heads and tails are the only possible outcomes, I expect at least 1 flower, 1 rose. Not possible, right? Because heads and tails are the only possible outcomes. So null events are those events which have 0 members. Therefore, the size of the null event is 0. Therefore, probability associated with the null event is 0. Because numerator is 0, denominator is finite. Therefore, probability for a null event is 0. Okay? Special event. Another special event is called the full event. Okay, what is it? Essentially, it says something happens. Okay, I toss a coin, and what are you expecting? I expect to see something. Okay, therefore, it could be HH, HT, TH, TT. Okay, which means that for the full event, something happens. The full event, the size of the full event is the same as the size of the sample space, because any one of those possibilities could be an outcome. Okay, therefore, the probability of getting a full event is 1, because the event is the same size as the sample space. Therefore, the probability is 1. You cannot have an event which is smaller than 0 members. Okay, you cannot have a negative members for a set. Therefore, probability cannot be less than 0. You also cannot have an event which has more than the sample space. Okay, the event cannot be bigger than the sample space. Therefore, the probability cannot be greater than 1. Therefore, probability always lies between 0 and 1, both included. Okay, so 0 less than or equal to probability less than or equal to 1. Okay, so that is the main property of probability. Okay, probability is a number that lies between 0 and 1, both included. Okay, this should be very easy. Now we are going to define some very special events. This is in terms of when we have 2 events, 2 or more events, okay, more than 1 event. Okay, we define events called mutually exclusive events. What does it mean? It means that if an outcome is present in one event, it is guaranteed to be not present in any other event, or in the other event, not any other event, in the other event. If you say 2 events are mutually exclusive, if an outcome is present in one, it is not present in the other, and vice versa. So biologically, for example, you say one event is, you have a set of people. One event you are looking at is the person is male. The other event you are looking at is the person is pregnant. Now these are mutually exclusive. These are mutually exclusive, right? So this is one set of special events. Okay, it is okay. We'll come to that. We'll come to some special meanings of this shortly. Some special findings of this shortly. Independent events. Okay, this is another type of event. Yes.
Just nitpicking here. Mutually exclusive event, I think is you mean to say event, not events, because that's what I was thinking of when you said events.
Events.
Like, yeah. One event. If one event happens, then the other cannot happen. But what you really mean is one event, if it happens, it cannot be, that same event cannot be present in another event. But when you say 2 events, it implies the existence of, 2 different, I don't know if you understand what I'm saying, 2 different events.
Yes.
That's when I looked at it, I was thinking, if one thing happens, then another event cannot happen. But what you mean is, if this particular event happens, then it can't happen. That outcome happens in one event. It cannot happen in another event.
Okay, I'm going to strongly discourage you from using the word happen. That's what I want to first get rid of. Rather, I would
Okay.
like to use the word present. Okay. If an outcome
Okay.
is present in one event, think of an event as a subset, as a set. Okay. So you have some, let's say we have some names here. Okay. Tom, Jerry, Mike, one set. There's another set. Okay. Eve, Apple, and Stella. Okay. Two sets. Okay. Now I randomly pick one person from these 6 people. Okay. Let's say then these two events are such that if an outcome is present in one of these events, it is not present in the other. Let's say I pick the person Tom. Tom is present in set A because the set A had Tom, Jerry, and Michael. Whereas the set B had Eve, Apple, and Stella. Okay. So I know, the moment I know that Tom is present in event A, Tom is not present in event B. That has become obvious because these two are mutually exclusive. Okay.
Okay.
On the other
So,
hand,
what?
Yeah, go ahead.
Yeah. On the other hand, you can have a situation because of certain relationship between the two outcomes. Let's say where Tom is present in one, and if Tom is present in one because of a relationship with Apple outcome, you could say that it could be that if Tom is present in event 1, then Apple is not present also in event 2.
No. It's
That's
not
kind
that.
of what I was looking.
No.
Yeah.
It's not that. Okay.
Okay.
Mutually exclusive.
I
Okay. I think it should become clearer in the next slide. Okay.
yes.
Just hold on, because I'm going to show some pictures that might make it easier to follow. John Sirani, you had a question.
Yes, Rajan, what I just interpret in this way, connecting with the ML algorithms, might be when we are identifying the spam emails, if one email is categorized as a spam, okay, then that same email could not be spam. So that's what you mean to say.
Excellent.
Exclusive.
Excellent.
So,
So I want to stop here and say, make it a little bit bigger. Look at all the spam emails and look at all the non-spam emails. If an email is present in the spam folder, it is not present in the not spam folder, and vice versa.
Got it.
That's the mutually exclusive events. Okay. Let's finish mutually exclusive events. So, okay, I don't want to look at this. Here is a mutually exclusive events. Okay, you have a sample space. The sample space I'm going to denote by this blue oval, and there is an event A, and there is another event B. Okay, I have drawn it such that you see they do not have any common area. There is no common members are there between these two. Therefore, in this sample space, if you pick a point and if it's present in B, because they are mutually exclusive, we know it is not present in A. Likewise, if it is present in A, it is not present in B. Okay, so that's what I was telling about when I'm talking about mutually exclusive events. Let's take some examples. Here is one example. Set of all multiple choice questions with only one correct option. Okay, with only one correct option. So 4 options. Each question has only one correct option. 3 of them are incorrect. Now, if you look at all this set of questions, which has option A as the correct option. Okay, that's called set A. Let us say that's the event set A. Event B is the set of questions where option B is correct. Therefore, if one question is present in set A, it is definitely not present in set B, and vice versa. Right? So this is what mutually exclusive is about. Jeff, does that make clearer?
Sorry, I have to take my mic off. Yeah, it's clear. I guess I'm kind of thinking of like again. It just goes to like mutually exclusive uh, event versus events. Like the idea of like I mean, what I'm thinking of in my head, and I'm still trying to flesh it out, is say a conflict of interest. Let's say, right? Applying the concept of mutually exclusive events, and I was just trying to see how I'm not like in terms of this diagram actually too. I was trying to see where you have, you know, two events that are associated. Let's say, right? Not just one event. I understand what you're talking from what you're saying right now. It talks about one particular event, and then the idea. What was getting confused in my head was the two events that are associated um, in some kind of a relationship, and I'm having a hard time explaining.
They have a relationship. Definitely, they have a relationship.
There's a relationship, and if one exists in one, let's say, like I say, in a conflict of interest in a company, let's say a non-compete situation, you know, if that is broken, if that rule is broken, right? If one partner exists in another company, then that mutual exclusivity is broken. That rule, let's say, that's kind of what I'm thinking about in my head.
So let us say you are freelancing for two companies. Okay, you have a set of projects for company A and another set of projects for company B. Okay, now your within quotes conflict of interest prevents you from working on similar projects for the two companies. Okay, so
yes,
now if I look at the projects that you are working on, let's say, you know, some let's say finance related project. Okay, if that falls in company B, it is now clear you do not work on any finance related project for company A. That's mutually exclusive.
Right.
Okay, so that's what it is.
Okay.
Okay.
Okay, good. Thank you.
Okay. Now, mutually exclusive events in terms of probability, how we define that is an event can be either in A or in B. Okay, that's what it says. An event can be either in A or in B. If you look at that question, then that question leads to this equation called, it is probability that the event is in A plus probability that the event is in, sorry, the outcome is in B. Okay, probability for the events A or B is equal to probability of A plus probability of B. So this is the definition for mutually exclusive events. Okay, that's another definition, actually a much better definition, which will come in a short while. Let's actually see that. A true definition is this: the probability that an outcome belongs in A as well as in B. Okay, and an outcome belongs in the event A and B. If you look at that probability, if that probability is 0, then we know A and B are mutually exclusive. Okay, A and B are mutually exclusive. So this is the definition for mutually exclusive events. Okay. Now, here is an example. No, customer event A for a bank, let's say. Okay, customers who default on loans. Event B, customers who are high net worth individuals. Okay, are they mutually exclusive or not? And here we are not going to use any of this mathematics, but we are going to use our understanding of these things. Okay. Customers who are net high worth individuals, some of them could also default on loans. Right? That's where we find frauds. Right? So this is not an example for mutually exclusive events. Okay? Just a silly example, just to give a counter intuitive idea. Now let's go back and look at another event. So mutually exclusive means if an outcome is present in one event, that outcome is not present in the other event. If that is the case, then these two events are called mutually exclusive events. There is another set of events. Let's say another two sets of events. One event A, another event B. Okay. If you take some outcome, it can be present in A, it can be present in B also. Okay. But whether it is present in A is not, whether it is present in A or not, is not dependent upon whether it is present in B. Okay. The presence of one outcome in one event does not influence the presence of the same outcome in the other event. Okay. So here is an example. You are looking at a set of children in a school. So you are looking at the set of children whose father was born on a Monday. Okay. The set of then event B is the set of children whose mother was born on a Monday. Okay. So some children can be present in both A and B. But whether they are present in A does not tell us anything about whether they are present in B, and vice versa. Okay, that is, if we whether a child's father was born on Monday or not does not tell anything about whether the child's mother was born on a Monday or not. Okay, so these are truly independent events. Okay. Now let's think about this other example. A person belongs in event A. That definitely precludes this person from being present in event B, and vice versa. Therefore, whether a person is present in event B depends upon whether the person is present in event A or not. Okay? Therefore, mutually exclusive events are definitely not independent events. Mutually exclusive events are definitely not independent events. Okay, this is very important. Now let's look at some example of independent events. The examples I'm going to give are kind of heuristic, theoretical, but mathematically all these examples could fail. Okay, with that caveat, let's say take a look at it. So what does it mean? When we have, see, independent events are not mutually exclusive, or mutually exclusive events are not independent. Therefore, event A and event B will have some intersection, will definitely have a region of intersection. Right? Some will be present in A, and the same will also be present in B. Right? So let's take a look at an example. In a truly idealistic world where students do not copy from each other, let's say the set of event A is the set of questions for which student A gave the correct answers. Event B is the set of questions for which student B gave the correct answer. Okay, so these two are independent events in the exam. Okay, because in a truly idealistic world, again you can reason out that they need not be independent. Why? Because if they came from the same socioeconomic background, if they have the same study habits, and if they are in the same class, right, then it is highly likely that they would answer a given question in a similar fashion. Therefore, these are not truly independent, but let's say, this could be one such example. The mathematical expression for these kind of events, where an outcome can be in event A or in event B, when these two events have some intersection. Okay, the probability is given like this. Why? When we look at event A, we are looking at this entire yellow region, and when you're looking at event B, we are looking at this entire grayed out region. In this sense, we are counting this intersection region twice. Therefore, we have to remove it once. Okay, so that's why we have minus P of A and B. Okay, so since for mutually exclusive events, P of A and B is 0, P of A or B is equal to P of A plus P of B. That's why we got that expression earlier. The true definition for independence is not the first equation, but the second equation. Okay, the second equation. What is it? That the probability that an outcome is present in A and B is the product of the probabilities, P of A times P of B. This is the this is the definition for, this is a check for independent events. This is a check for independent events. Yes, John Sirani, please go ahead.
So, Rajan, could you please you give the same P and probability of A and B in the mutually exclusive? Is it, what is the formula you written there? Could you please just to show that screen also 1 minute? Yeah. Okay, it's 0 there. Okay, thank you. Yeah.
Yes, somebody else also raised the hand. Please go ahead, ask your question.
Yeah. Sir, can there be independent events without any intersection?
No, there cannot be. If there is no intersection, then what happens is P of A and B is 0. Correct? That is, an outcome present in A and also B becomes 0. The probability of that becomes 0.
Then they become exclusive, is it?
Then they become exclusive. So exclusive events mean they are dependent on each other.
Okay.
So for mutually exclusive events, the left-hand side will be 0. If neither one of them is a null event, A is not a null event, B is also not a null event. If that is the case, then P of A times P of B is non-zero. Right? Only for null events, probability is 0.
Got it.
So this is non-zero on the right-hand side. For mutually exclusive events, this will be 0 on the left-hand side. So the condition fails for mutually exclusive events. Therefore, mutually exclusive events, independent events will definitely have some overlapping regions. So they will have some common elements. So here is another example. It's another silly example. Customers who default on home loans. Customers who are software engineers. So we cannot say anything about it, whether it is right or wrong. Now, whether these two events are independent or not, we cannot say anything unless we check this condition. Okay. Okay. So I leave it as a question mark. Okay. Again, a very poor animation. Or mutually exclusive events and independent events clear? Or you can think of it this way. Any set of events that satisfy this equation, they are independent events. Any set of events that satisfy this equation, they are mutually exclusive events.
So, Rajan, in this case, if P probability A or B, it sometimes or all the time, is it 1 or it is sometime 1? Because if we count P of A plus P of B.
See,
It's
if
one, is it? Yeah.
P of A plus P of B is definitely less than 1 in situations like this.
Yeah.
But
Dissect.
if you dissect the sample space, where one side is A and the other side is B, or the entire sample space is split into two groups, where one group is A, the other side is B, then this will be equal to 1. P of A plus P of B is equal to 1.
Understood. If I have a mutual exclusive events, like Jeff mentioned, then it has become like a 3 events, then it could be like a different case. Yeah.
Yes.
Understood. Thank you, Rajan.
Look at this question then here. Okay. The whole sample space is divided into 4 parts. One part where the set of questions has option A as the correct one. Second part is the questions that have option B as the correct one. Third is option C, correct. Fourth is option B, correct. So the entire sample space is divided into 4 parts.
Great.
And each one is mutually exclusive with each other.
Understood. Thank you, Rajan.
Yeah, sure. Okay, now I'm going to talk about another very, very important concept called conditional probability. This is very important because this forms the foundational idea for everything that we are going to talk about from now on. Okay, so what is it? Let us say we have some experiment, so its sample space is known, and we have 2 events. Now we are considering 2 events, and we are looking at one outcome, and we know that this outcome belongs in event B. Okay, the outcome is a member of event B. We know that. That's we have known now. Now I ask the question, what is the probability, once this information is known, what is the probability that this outcome is present in event A also? Okay, given that the outcome is in event B, what is the probability that the outcome is in event A? Okay, so what are we looking at? We are looking at actually something that is present in both A and B. Correct? We are looking at something that's present in both A and B. That's clear because it's given it's present in B, and we want to find that's in event A. Okay, so we want to see something like this, probability of A and B. That's what we are looking at, something like that. But then we have to use this information. We know already that the outcome is in event B. So how do we do that? Okay, so let's look at this particular diagram. Okay, it's the same diagram as before I drew for independent events, slightly distorted now. So let us say the outcome is in event B. Okay, the outcome is in event B, this grayish area. Okay, therefore now I want to ask, what is the probability the outcome is in event A also? Okay, that means this particular outcome cannot lie in this area, that's in the area of A, that's outside the intersection. So I am looking at only the intersection area, right? Only this intersection area. That's what I'm looking at. But I want to find this intersection area in relation to this B, in relation to this event B, not with respect to the entire sample space. Because now I have given this, it is present in B, I have to find out something about this intersection area. So essentially what I want to do is, I am asking the question, probability that the outcome is in event A, given it is in B, is essentially, I want to find what is the probability that it is in this intersection area, given that it is in event B. So now I can think of event B as my sample space, and the intersection area as my event. So the size of this intersection area divided by the size of the event B, that's the probability I'm looking at, right? So a very bad animation, so forgive me for this. So let me go and look at this. Okay. So what we are looking at is, we are looking at the size of the intersection, which is n a times a and b divided by the size of the event b. That's all I'm looking at. Now I can convert this into probability. How? Divide the numerator and denominator by the size of the sample space itself. So this is called multiplying by 1. Both numerator and the denominator are divided by the same number, right? Divided by the same number. So I just have, I have not changed anything. I just multiplied by 1. So the numerator therefore becomes P of A and B. The denominator becomes P of B. Okay. That's all there is to it. So if we want to find out conditional probability, that if we already know some information about an outcome, we can use that information to calculate the probability that it is in some other event. And that is given by this. Probability of the event A given event B is probability of A and B divided by probability of B. Okay. It's a straightforward, if you look at this picture and look at this particular equation, the first one, it should be obvious now. However, if we flip the question, given that the event is in A, what is the probability it will be in B? It is again the intersection divided by the area of A. Okay? That is probability of A and B divided by probability of A.
Excuse me.
Right.
What's N? Again, please.
Say it again.
What is N?
N is the number of, the size of this set, number of elements.
Right. Okay, good. Thank you.
Number of members of this set. Thank you. Thanks for asking that. I should have written it somewhere. Okay. Now, so how we write this is important, because depending upon how we write it, the probability will change. Probability of A given B is probability of A and B divided by probability of B. Probability of B given A is probability of A and B divided by probability of A. See, these two are different, right? The denominators are different. Therefore, these two conditional probabilities are different. Just a definition. Again, why are we going to use this? We'll come to that in a very short while. Okay. Okay. Straight away, we have come to this question. You can. I'm going to leave it as an exercise for you. Try it out. Okay. It might be fairly easy. Given that a car in the empty cars data that I showed earlier yesterday has a fuel efficiency greater than 15 miles per gallon, find the probability that it has more than 4 cylinders. Okay. Find the probability that it has more than 4 cylinders. Maybe let's take a look at this problem. Maybe I'll solve it for you so that you get an idea of what this conditional probability is all about. Okay. So let me go here. Open. Empty cars. Okay, I'm going to open this, save it for, say just today's date. Save as. Since this is such an old data set, we have been using it for a long, long time. 6 empty cars. Okay. So what I'm going to do here, I'm going to copy this. Sorry. Here is the data. Okay, I have downloaded the data. and let me copy it here. Let it all be there. Bigger. Okay. So I do not know whether they, yeah. Okay, good, awesome. Okay, so we have this different things. What is the question we have? We have given that a car in empty cars data has a fuel efficiency greater than 15 miles per gallon. So I'm going to find those cars. Okay, what are those cars? MPG greater than 15, right? That's what we want to know. So I'm going to write if where is MPG greater than 15, then it is 1, otherwise 0. Okay, so that's what I'm going to do. So I have some number of cars. Okay, so what I have done is I have given a value 1 if the MPG is greater than 1, sorry, greater than 15, otherwise it's 0. 15 or less, I have given it 0. Okay, so how many cars have values MPG miles per gallon greater than 15? All you have to do is add all these values. That's all. So there are 26 cars out of 32. Out of 32 cars, 26 cars have MPG values greater than 15. Okay, this is what is this? This is our event A. This is the given event. This is the given. Now let's look at this is the condition. Now what is the other one? The other one is number of gears, right? More than 4 cylinders. Okay, still greater than 4. Let's take a look at it. So if cell greater than 4, it is 1, otherwise 0. So let us take a look at it. So here it is. Again, I'm going to do the same thing. Count the number of cars that have cylinders greater than 4. Okay. Now, what I have to do? I have to calculate if 15. If MPG is 15, how many of the cars with MPG 15 have cell greater than 4? Correct?
Your mic is not on right, I think, maybe again. I don't know if everyone else there, that's better.
Okay. Is it better now?
Yeah, way better. Yeah.
Okay. So now what we want to do is we want to find out of all these 15, out of all these cars that have MPG greater than 15, how many has cylinders greater than 4, right? So what is it? So we need to find MPG greater than 15 and cyl greater than 4. So what do we do? So we say this times this. All you do is multiply. Both should be present, right? This is the AND question. So how many are there? This is again. So 15 cars that have fuel efficiency greater than 15 miles per gallon have more than 4 cylinders. Okay. So what is the probability now? So probability that cyl greater than 4 given MPG greater than 15, what is this equal to? This is equal to probability cyl greater than 4 and MPG greater than 15 divided by probability MPG greater than 15. Correct? This is our conditional probability. Or we can go and do this one, numbers, right? Whichever way we want, we can do. So what is this? So what is probability? Probability of SIL greater than 4 and MPG greater than 15. What is this? This is equal to this 15.
15.
Sorry. This is equal to, this is the joint
Intersection
probability,
is
that is
15.
the intersection probability divided by what is the this is the number of cars with this condition. What is the total number? 32.
15.
Right? 32. So I'll just write 32. So this is the joint, this is the numerator. And what is the denominator? P of MPG greater than 15. This is equal to, greater than 15 is this, divided by 32. So our P of A given B, or let me write P of SIL given this is equal to this divided by this, 0.57. Okay. So what does it mean? Let's look at this. Okay. Out of these 26, 15 have both. Let's check that. Okay. So 15 over 26 is this number. Okay. This is what I was talking about. So this is, so you can see now how, if you ask some other question, if you ask only this question, the probability that number of cylinders greater than 4 and the MPG greater than 15 is 0.46. But the moment you know this MPG greater than 15, the probability that the SIL is greater than 4 has improved. Given that information, this has now improved. Right? We have much more confidence of saying, yes, this number of cylinders is greater than 4. Yes, Suvir Bajaj, please go ahead.
The question is, since cylinders greater than 4 is the condition in this example.
That's not the condition.
Oh, it's not
MPG
the
greater than
condition.
15 is the condition.
Sorry. MPG greater than 15 is the condition in this example, and you've already arrived at 26 as the count for that condition. Why couldn't you just simplistically divide 15 by 26 to arrive at 0.57?
Exactly, you can do that. That's
you
what
can do that. Okay, that's not incorrect. Okay, understood.
That's not incorrect. That's correct. See,
okay,
this
got
is the using the formula. I have derived this first one, but the second one, okay, the second one is n of
got it. Thank you.
Greater than 4 and MPG greater than 15 divided by n of MPG greater than 15. Okay. That is this 15 by 26. Okay. If you look at the formula, it will say 15 is in the numerator, blue color, 26 in the denominator, red color. Okay. So that's what it is. So what you say is true. That's what I have done. Just as a demonstration. This is a very silly demonstration for conditional probability. Let's take a much more meaningful exercise. Okay. What do I mean by that? What happened? I think my laptop is possessed. it's moving by itself. Okay. So here is a slightly more meaningful question, okay, which is something that we always do. About 4% of the population is known to have a particular disease X, whatever the disease is. Okay, a medicine B is used to treat X. Okay, 92% of people who take the medicine get cured of X. Okay, what is the probability that the person who does not have X, who does not have the disease now, took the medicine? You see people, okay, randomly you pick a person from the population and you find that this person does not have the disease. Let us say it's a seasonal flu. Okay, currently this person does not have seasonal flu. This person does not have the seasonal flu because he did not get infected. That could be one possibility. Or he got infected, took the medicine, and now he is free of the disease. Two possibilities are there. Okay, now I am asking the question, given this person does not have the disease now, what is the probability he took that medicine? Okay, this is a kind of a question that public health people would deal with. Okay, let me give a slightly different example. Okay, this is something that we can easily relate to. No, in the pandemic days, almost all of us probably bought this IR, what do you call, saturated oxygen saturation monitor, right? SpO2, we call it, the blood oxygen saturation point, right? Many of us would have bought that, and some of us still possess them. Some of us might have thrown that out. So now what happens is, we know that when this number is greater than 96, when it shows 96 or more, it's a partial pressure, so it's in percentage. So if it's greater than 96%, then it's normal. You have normal oxygen saturation. Okay, if it is less than 96, go check, talk to your doctor. That's the thing. How do we know that 96 is the correct number? Because the manufacturers, they have looked at two kinds of people. One kind of people who had normal oxygen, blood oxygen level, people who had lower blood oxygen level than normal. So they have these two sets of people, and then they have measured, they have used this instrument on both sets of people, did some calculations, and then have come up that if this number is less than 96%, then you are in the group with less oxygen. If it's greater than or equal to 96, you are okay. Okay, that's what it says. Is it 100% the case? That is everybody who has normal oxygen level. Does this instrument say you are normal? Not necessarily. For a large proportion of the normal people, it would have said yes. It would have shown a reading greater than 96. For some people with normal blood oxygen level, it would have shown less than 96. Possibility is there. Likewise, the other way. For a large number of people who have less blood oxygen level than normal, it would have shown a value less than 96. For a few, it would have shown greater than or equal to 96. It's possible. That's what happens. So if you have worked in these instruments, any of you would know that, if you are from the healthcare clinical side. Now what happens is, we have this instrument, and then we measure somebody's blood oxygen level. It gives some number. Let us say it gives 96. Okay. Now, what is the probability that this person actually has less than the normal blood oxygen level? Okay. What is the thing that we know? Given the person has less than normal blood oxygen level, the probability of getting 96 or greater is 0.1. or 0.03. Very small probability. But we are now flipping. What is it? I have found a person who has a blood oxygen level of 96, and I want to ask the question, what is the probability that this person belongs in the less than normal blood oxygen level group? Right? So these are some very important practical questions. Physicians have to deal with these questions. They don't actually do these calculations. I know some physicians who do that, who calculate these numbers. Okay, but most physicians do not do that. They just go by mnemonics and assume the probabilities are strong. Yes, Suvir Bajaj, go ahead.
The question, I apologize if this is a juvenile question, but 92% of people who take the B get cured of X. Is that, so do we infer that 8% of people who take B do not get cured of X? Is it a binary inference?
Yes, correct.
It is. Okay,
It is.
thank you.
It is correct. Okay, so of the people, yes, Sam Leong, please go ahead. Sam, if you are on mute, please unmute yourself and speak.
All right. So can I rephrase this question like, what is the probability that a healthy person took the medicine?
What is the
Right?
probability that a healthy person took the medicine?
Yes.
Yes, that's another question we can ask.
Is equivalent to this question,
No,
right?
it's not necessarily equivalent. Okay,
Hmm.
because right now I know this person is healthy. Okay, but 5 days ago, whether this person was healthy or not, I do not know. He could have been healthy and continued to be healthy. He could have been unhealthy, took the medicine, became healthy now. There are two possibilities. Each has different probabilities. So I'm asking the question, given that now this person is healthy, what is the probability that 5 days ago this person was not healthy? Right? Condition is today this person is healthy. What do I want? 5 days ago, whether this person was healthy or not. That's the kind of question this is about. So what you said is one possibility out of two possibilities. I want to find probability for both of them. Okay, that's what. So these are the kinds of questions that are very practical that we can use. Let us say in the assembly, okay, in the assembly, you are in the assembly line, you randomly pick few objects, few of the products, and check for their quality. Okay, and it turns out that 8% of the products you tested turned out to be bad. Okay, so if 8% in the tested batch, tested group is bad, what is the probability that in the actual assembly, okay, the number of bad products or the percentage of bad products are 8 or more? The percentage is 8 or more. Okay, so that's the kind of question you want to ask. Given this condition, what is the probability there? Okay, so now you can immediately see we are going from simply playing with probability, we are going to, as someone talked about, samples and populations. We are trying to connect all these things. Okay, so yes, Ergard Greaves, I hope I pronounced your name correct.
That's perfect. So are we saying that conditionality?
Can you speak louder or get close to your mic?
Conditional probability is a tool that we actually use to measure independence and mutual exclusivity.
I have to stop you. I cannot hear you. Can you please come closer to the mic or speak louder?
Sure. I apologize. Are we suggesting that we can use conditional probability to infer independence or mutual exclusivity?
You hit the nail on its head. Yes. In fact, conditional probability is the one that helps us actually define independence. Okay. So, previously, many of our faculty with this upgrade program, with this GTU program, we used to be part of an institute called INSOFI. And in INSOFI, what we used to do is, it was done for these very early professionals, 1 or 2 years in the career. They wanted to learn AI, ML. So we had these programs. It was offline programs. So we would teach them in the class, very, modern by the standards of Indian classrooms. Anyway, what happens is whenever somebody in the class gives a very correct answer or makes a very intelligent comment, we give them a chocolate as an encouragement. Okay, so to you, Ergot, here is a virtual chocolate to you, maybe a box of chocolates, because before even I could come there, you correctly got the grip of where we are going. Yes, conditional probability is what defines independence. Okay, and this is where that comes from. Independence comes from conditional probability, but conditional probability also has many other usefulness, and that is what is called hypothesis testing. Okay, so we are going into multiple directions. What you said is very correct. I'm very glad that you said that. So here is another question. Given that a customer has bought an item A, what is the probability that this customer will buy item B? Okay, so here this is like recommendation system. This is exactly the question that recommendation systems will look at. So you look at all customers who bought item A and also item B, and then normalize with respect to the customers who bought item A. Okay, so that gives this conditional probability. So all these possibilities are there. As where is here it is. So we will finish this first. Independent events. Okay. So the occurrence of an outcome in event A is influenced by whether it appears in event B or not, right? That is, the occurrence of an independent events. Independent is influenced. No, it is not. The occurrence of an outcome in event A is not. It's not influenced by whether it appears in event B or not. This is independence. Right? This is independence. Independence means the occurrence of an outcome in event A is not influenced by whether it appears in event B. Right? That is, probability that an outcome is in given A, given it is in event B, is simply probability of A. It doesn't care whether it is in B or not. It is not, this probability is not influenced by the fact that the event B might be, the outcome is in event B or not. Therefore, this conditional probability is simply this. It's simply this. Right? Now, if that is the case, this conditional probability is also written as probability of A and B divided by probability of B. If we cross multiply this, we get probability of A and B is equal to probability of A and probability of B. That's it. This is the condition for independence. Right? So the condition for independence comes from conditional probability. Okay? The conditional probability, if it is not dependent upon the condition, right, then the events are independent. Okay? The condition has no effect on the conditional probability. If that is the case, then the events are independent. So that's what we have here. So that's how we derive this. Okay. We'll take a short break now. Okay, and when we come back, okay, let's finish this. It's very easy. That's another application of conditional probability. This is called Bayes theorem. Bayes theorem is nothing but, if we know one conditional probability, is it possible to find the reverse conditional probability? Okay, that's the question. We can do that provided if we know that these are called marginal probabilities, okay, or single event probability. Single event probability or marginal probabilities. If we know these probabilities, then of course we can do. How? The key is this. Probability of A given B is probability of A and B divided by B. Probability of B given A is probability of A and B divided by probability of A. You see the numerator in both these cases, they are the same. They are the same. Therefore, we can write probability of A given B times probability of B is equal to probability of B given A times probability of A, this equation. Therefore, we have this equation where we relate one conditional probability to the other conditional probability. Very straightforward. Very straightforward. It's a very elementary derivation. Okay, there is nothing big deal about it. But in the 18th century, when Bayes was a pastor, actually, he was a clergy, and he was working on numbers and probabilities, and in fact, he used to attribute this relationship to the work of God. Okay, how God speaks through mathematics, no, whatever. So he used to attribute a lot of different things, but he was the one who first derived this. 200 years ago, apparently these were very difficult relationships to understand. But anyway, irrespective of that, he first wrote this, at least in the Western world. So this is called Bayes theorem. Okay, and in fact, if you see, most of our probability, all our textbook examples of probability deal with tossing a coin or gambling, cards, etc. The reason is very simple. Probability in the Western world developed because these in the 18th centuries, the nobles, the British nobles, they wanted to know. They had a lot of when the Industrial Revolution was picking up, these people had lots of time in their hands. They were gambling, and of course they didn't want to lose, right, in the gamble. Therefore, they hired mathematicians, big names like Pierre de Fermat, like Gauss, like Hermite, all these big mathematicians. They hired these mathematicians and forced them to help them figure out a way to win these gambles, in these gambling games. And that's when these theories are developed, as we know now. And that's why you see a lot of textbook examples, or in the they use all these gambling examples. In fact, I have another example where I do not know whether it's part of this slide deck or not, where we show something about slot machines. But anyway, so whole of probability theory, as we know now, at least the ideas are expounded using these card games and tossing a coin, throwing a dice, all these things. Okay? Basically, because of the historical nature of the development of this particular field of mathematics. Anyway, so here is an example of Bayes theorem. This is the most important example. As I mentioned, a medical equipment manufacturer tested a new instrument on some people with a particular condition, blood oxygenation level, and found that 92% of the times this instrument detected the condition correctly. That is, out of 100 people who had this condition, it correctly detected 92 of those people. Okay, it is also known that 7% of the population has this condition. In the population, 7% has a condition. That's a given. So P of condition, the condition is the person has this particular disease. What is the probability that this person has a disease? That is 7%. That condition is given. Given that a person has this condition, given that the person has a disease, the probability that the instrument is able to detect it is 0.92. Right? Given the person has a disease, the probability that the instrument detects the disease is 92. Now we ask the other question. In the clinic, we are not doing that. In the clinic, the instrument detects the condition. The instrument says that this person has a disease. You prick your fingertip, check it with your glucose monitor, and then it says you have high blood sugar level. Blood sugar level greater than 126 milligrams per deciliter. It says 140, let us say. Now you are scared whether you have diabetes or not. Okay. So what is the question the clinician asks? Given that this instrument detects the disease, what is the probability that the person has the disease? See, the condition is flipped. Right? Originally, what we have is, given the person has a disease, the probability the instrument will detect is 92%. Now, what are we asking? Given the instrument detects the disease, what is the probability that the person has the disease? So it's a reverse curve, P of A given B. From that, we want to go P of B given A. How do we solve this problem? We solve this problem essentially using Bayes theorem. What is the Bayes theorem? It says this: probability that the person has the disease given that the instrument detects it is equal to probability the instrument detects it given the person has a disease, and the probability that the instrument, the probability that the person has a disease. This is the 7%. This is the 92%. But this information is giving. What is the probability that the instrument will say that somebody has a disease? And that we need to know. Once this information is known, we could calculate this. Okay. So this is the way the probabilities work out in real life. No? And what we will do is we will take a short break now, and we will move on to studying how we put these ideas together and start asking more important questions. Okay, like the question that we discussed yesterday. Okay, we alluded to these questions yesterday. We will discuss these questions in depth today. Okay, so I'll stop. I'll stop my. What is the time now? Let me check. Okay, the time now on my watch is 8:02 p.m. So in 13 minutes, let's get back and take a look at this question. Okay, so we'll have a short break. We'll have a 13 minutes break and be back. Okay, thank you. Okay. Fine. We are now at a correct juncture to talk about something very important in all these things that we are doing. The reason for studying statistics and probability is for us to understand something about what we call as a population. What is it? For example, this is an example that I like to give in other classes. Let us say a particular state government is planning on coming up with some kind of a midday meals plan for high school children. Okay? So they want to know the current nutritional status of the children of the high school children in the state. So that could run into a few 100,000 or a couple of millions, depending upon which state we are talking about, or more than few millions. Okay, which country, which state, it depends upon that. But therefore, what happens is this: the state cannot enumerate the nutritional status of all children. Therefore, what it does measurements on a small subset of the children. And then from the measurements made on this small subset, it wants to infer, make some decisions, make some plans for the entire set of high school children in the state. Right? So we have two different sets here. Set of all high school children, that's called the population in this situation, and the set of small sample, okay, the set of maybe 800 students, 800 high school children on whom the state measured their nutritional and health status. Okay, so that's called the sample. That set is called the sample. So we have a population which is the entirety of whatever we want to study. And the study on the population, when we make some studies on the population, and whatever numbers, whatever quantities we get with respect to the population, those are called the parameters. Okay, parameters for population, P for P. And those are usually denoted by Greek symbols, Greek letters. Okay. So for example, we could find the mean value for the population and we would denote it by the symbol mu, or the variance denoted by the symbol sigma squared, or the proportion denoted by the symbol pi, whatever, right? So parameters, Greek symbols related to population. And the process of making the measurement of the population is called the census. When we say census, that means we are making measurements on each member of the population. Okay. While doing the census could be very difficult on multiple grounds, maybe not enough time, not enough resources. And in reality, what could happen is, in some situations, when we start the census, and by the time we finish the census, the property of the population might have changed. Okay, so things like that could happen. So usually, we do not resort to census, but only make measurements on a small subset of the population. This subset is called the sample. The subset is called the sample. The quantities that we measure on the sample. Those are called statistic without the plural form of it. Statistics is a study. Statistic is the quantities, is the quantity related to the sample. For example, and these are denoted by the English alphabet or Roman alphabet, right? So we could measure the mean for the sample, which you would denote by the symbol M, or usually X with a bar over it. Okay, capital X with a bar over it. That's the usual symbol for mean. But for variance, we use the Roman equivalent of the Greek symbol, sigma S squared variance. Standard deviation is just S. Right? Proportion, we use the symbol P. In population, we use the symbol pi, like that. The process of measuring on the sample is called survey. So survey for sample, statistic, okay, all this, it's easy to remember. Statistic refers to sample, and survey means measurement of the sample. Census means measurement of the population, and the quantities related to the population are parameters. They are represented by Greek symbols, whereas statistic are represented by English letters. Okay. Now, having said this, what could go wrong? Why do we do this? The reason we measure the sample statistic is because we want to say something about the population parameter. Right? We want to know how all the children in the state, what is the nutritional status of all the children in the state. But we only have the nutritional status of the sample. So from the sample, we want to go to the parameter. Okay. So how do we make this connection? So here is an example. You sample 36 apples from your farm's harvest of 200,000 apples. So this 200,000 apples is your population. Okay. But you cannot measure on all the 200,000 apples, so you measure on 36 apples. And what do you get? For these 36 apples, you get the sample weight, the mean weight. It should be called mass, but let's say anyway. Mean weight is 112 grams, excuse me, with a standard deviation of 40 grams. These 36 apples have a standard deviation of 40 grams in its mass and 112 grams as the mean mass. Now, can we say anything about the mean of the population mass, population? Okay, if you take the mean of all the 200,000 apples, can we say what its mean could be? Would it be 112 or what would it be? Okay, that's the kind of question we want to ask. Can we give an answer to this question? What is the mean weight of all these 200,000 apples? We cannot say that. We don't have that information. So what do we have to say? We say, okay, I'm looking at these 112 apples, I look at these 36 apples, from which I get the mean to be 112 grams with a standard deviation of 40 grams. Now, what I'm going to do is, I am going to hypothesize that my population, this population, has a mean value of 120 grams or 125 grams, whatever. So I make a hypothesis on the population. I have the details about the sample. Now what do I want to do is, I want to find whether my sample provides enough support for my hypothesis. Hypothesis about the population. Okay. This is what we really want to do. This is what we actually want to do. Right? In real scenario, in real life, this is what we do. We can measure, let's say you are in a you are let's say an automobile spare parts manufacturer. No, let's say you manufacture these nuts, and they have to have a diameter of let us say 8 mm. Okay, 8 mm. And manufacturing nuts, you are going to manufacture hundreds of thousands a day, right? And so what you're going to do is you are not going to measure on all of them. All you're going to do is every batch you pick out a few, make a measurement of them, and see whether they are within your tolerance that you have set. Okay, in one batch you find that the mean value is 8.3 mm with a standard deviation of 0.4 mm. Okay, now you want to hypothesize whether that batch, entire batch, its mean value is 8 mm. But your data says the mean of the sample is 8.3 with a standard deviation of 0.4. Your requirement is 8 mm. Okay. Now, is that hypothesis 8 mm? My batch average is 8 mm. Does that hypothesis now valid or not? So those are the real questions that we deal with, right? I'm sure some of you might have dealt with those questions in your career. Okay. So how do we deal with those questions in reality? You see, these statistical tools, all you need is whatever you have learned so far. That's all we need. Okay. So let's see what we have, how we answer this question. Okay. So here is the question I asked about. And so for this, what we have to do is we have to find from this sample data, we have to find what is the probability of getting the mean value for the population to be greater than 120 grams. If the probability is high, then I have a strong evidence for my hypothesis. Otherwise, if the probability value I get is small, then I don't have enough evidence for my hypothesis. If the probability value is small, I have to reject my hypothesis. Otherwise, I don't have to reject the hypothesis. Okay, this is the procedure we take. Okay, so what is meant by small p-value? We set a threshold. If the probability is less than 5%, the threshold is called alpha. If the probability value is less than 0.05, that is, if the probability is less than 5%, then we say it's a small probability and then reject the hypothesis. If it is equal to or greater than this, then we don't reject because the probability is not small. Okay? So that's the idea. Okay? So where do we get this? If we need to calculate probability, okay, I need to have what is probability? Probability is the size of the event divided by the size of the sample space. Now, what am I asking? I'm asking, what is the probability that the population mean is greater than some number? Okay. So now I have to get some idea of how much can the population mean vary. What are all the values the population mean can take? Once I get that idea, Then I can find, okay, beyond this number, how many are there? So that is my event. Total size that I can calculate. If I know the entire range, then I can do one over the other. Right? That's what we have to do. So how do we do this? This seems like that doesn't mean that the population mean. In reality, for these 200,000 apples, there can be only one value. If I measure all of them, there can be only one value. But what do we mean in this case? What is it that we are trying to understand? Okay, and this question is answered by, I'm going to skip this thing, and I'm going to go directly to what is called central limit theorem. Please give me 1 second, please. Just give me 1 minute, please. I'll be back. Okay, I'm back. Now I ask the question, okay, I took one sample of 36 apples and I found the mean to be 112 grams with standard deviation of 40 grams. If had I taken a different set of 36 apples, would I have gotten still the same 112 grams as the mean?
Might not, no?
Might not. Might not. Very good answer. Okay, might not. Okay, and if I take one more sample, again I could get a different answer, right? So let us say I have a large number of samples. One set of 36, another set of 36, another 36, another 36, another 36, so on and so forth. Okay, out of these 200,000, let us say I have 100 samples, each of size 36, let us say. Okay, therefore from each of these samples, I have a mean value. I have a mean value. And I also have standard deviation. Right? I also have a standard deviation. Now, we ask the question, okay, all these means, they are not going to be the same. They are going to differ slightly. Okay, they are going to differ slightly. If I plot the histogram of these mean values, I have 100 mean values. If I plot the histogram of these mean values, how will the histogram look like? And the answer to that question is central limit theorem. The central limit theorem says that if you have a large number of samples and you take the means from all these samples, then these means will fall on a bell curve, will fall on a normal distribution. When you have a large number of samples, when n is large, when you have 100 samples, when you have 500 samples, when n becomes large, the distribution of these sample mean values fall on a normal distribution. Yesterday, we saw that the normal distribution has a mean and a standard deviation, right?
Mm-hmm.
So, what is the mean of this normal distribution? And when people also probe that question, the mean of the sample means will be equal to the population mean. That's the first statement. The mean of the sample means will be equal to the population mean. Okay, this is remarkable. Why? So even though a single sample does not tell us anything about the population mean, if we take a few samples and take the mean of all these means, 136 set, one set of 36 samples, 112. Another set of 36 apples, 114. Another set of 36 apples, 132. Another set, 120. Another set, 118. Another set, 122. So on and so forth. When you take the mean of all these, that mean will be equal to the population mean. That mean will be equal to the mean of all those 200,000 apples. That is the first statement of central limit theorem. Central limit theorem. Okay.
So here,
So,
so for the central limit theorem, what's a reasonable n sample for a population that's a
n tends to infinity.
as
See, no, the thing is, it is there is no guideline on what n should be. So as long, what happens is this: when n is small, the histogram looks very different from a normal distribution.
yes.
And as you keep increasing n, it starts looking more and more like a normal distribution. And that number which satisfies you, in the sense, okay, this is normal for me. That is enough.
Probably here is where domain expertise comes into play.
Domain expertise comes into play. Correct.
Okay.
In fact, one of our colleagues, he doesn't teach in this program anymore. Praful Chandra, you could search his name. He used to say, remarkable teacher, and a great scientist too. And he always says many questions. He always says his answer would be, that depends. That depends. Yes, Prince, please go ahead. If you are on mute, please unmute yourself, Prince. Okay, so the distribution of the sample means will fall on a normal distribution, and the mean of this normal distribution will be equal to the population mean. Fantastic. Okay, now what is it? These are all means obtained from the samples. No sample mean is expected to be falling exactly on the population mean. Some will obviously fall. Okay, but let us say somehow theoretically you have this sample, this normal distribution. Okay, and you have one sample now, one sample of 36 samples. Okay, that will be different, maybe different from the population mean. Okay, now how can you quantify this difference from the population mean? You can talk in terms of the standard deviation of this distribution, right? How many standard deviations away from the mean is your sample mean? You could say that the standard deviation of this distribution is called the standard error of the means. You will hear the term standard error. Always, it's a short form for standard error of the means. That means in this distribution of sample means, what is the standard deviation? Okay. Now here is the kicker. I do not know whether okay, here is the kicker. Okay, let me write those down. Let me insert query object, form object. Okay, I'm going to say sigma underscore okay is equal to s square Let me make it big. Rules, format, font size. Font. Yes. Okay. Yeah. The standard deviation of this sample distribution, that's called the standard error of the means. That's denoted by the symbol sigma x bar. I put here subscript x bar because is the standard deviation of the means. Okay, standard deviation of the means. So it's called standard error is equal to s over square root n. What are these numbers? These numbers are, we have one sample. In that one sample, we have some standard deviation. That is this s. And the sample, we had some sample size, 36 in our case, right? So that is n. Okay. So in fact, I can write this out as sample standard deviation over square root of sample size. What happened? Square root of sample size. Okay, I'll do it this way. Okay. So sample standard deviation divided by square root of sample size. Okay, this is a very useful trick. Therefore, what we can do is, now let's think about this. To get the population mean, we anyhow have to do a large number of samples. But let's make a hypothesis. Once we make a hypothesis, we can draw the distribution of sample means because we know the standard error of the mean. The standard of the mean is given by this number, sample standard deviation divided by square root of sample size. So with that sigma, we can draw the bell curve centered at our hypothesized mean. Correct? So centered at our hypothesized mean, I could draw this distribution of the sample means. Okay? So this is one standard error, this is two standard error, so on and so forth. Okay? Now here is the kicker. What is the kicker? Now let us say my sample mean, my actual measured sample mean, this is my hypothesized population mean, where this vertical arrow is. My hypothesized population mean is here. My measured sample mean, let us say, is somewhere here. This red line. Here or here, let us say. One of these. No, red line. Red vertical line. Now how can I now tell, can you tell me whether I can reject or not reject this population mean looking at this graph? Okay, let me do one thing. Let me make it simpler. Duplicate this slide, go here, and I'm going to delete this. Okay, let us say this red is my population, is my sample mean, the one that I have measured. This is the distribution of sample means with the hypothesized population mean at the center here. Okay, how can I say that my data, this value, this one value I have, this one value, how can I say has a support for this hypothesized population mean? How can I say that?
It's still within 95% confidence interval.
I do not know what confidence interval is. Let's tell me just by looking at the graph. Give me some layman's interpretation.
Is it like 2 standard deviations away?
If it is 2 standard deviations away, what will you say?
It's far. It is far.
It is far.
Yeah.
All you want to look at is, I catch on that word far. All you want to see is how far is my population, my sample mean, my measured sample mean is from the population mean. If it is far away, then I reject the hypothesis. If it is close by, I don't reject the hypothesis. What can I set as far away or close by? Our 2 standard deviations. This is where our 0.05, the alpha, comes into play. Here is 2.5%. Here is 2.5%. Since it's symmetric, I don't care whether it is on the right hand side or the left hand side. All I'm saying is it is within 2 standard deviations. As long as in the sample distribution, my measured sample mean is within 2 standard errors, then I cannot reject the hypothesis. If my sample mean, on the other hand, is greater than 2 standard deviations, 2 standard errors away, then I reject. Okay, so instead of being here, is here in this case, let me say, what is this? Let me say, I will not reject. Okay, but on the other hand, when this moves to some other position like this, when my sample is greater than 2 standard errors away from my hypothesized mean, then I indeed reject. Reject what? We are not rejecting the sample. Sample is something we measured. We cannot reject. We can only reject the hypothesis. What is the hypothesis? Hypothesis is about the population mean. So we reject our hypothesis about the population mean. Okay, and the value from this lower end of the 2 standard errors and upper end of the 2 standard errors, this is called the confidence interval. Okay, and looking at where this sample lies. So if the sample lies within the confidence interval, you do not reject the hypothesis. If the sample lies outside the confidence interval, you indeed reject the hypothesis. Okay, so that is what. Yes.
Yeah. So confidence interval? Did we? I don't know. I kind of maybe I missed a couple of points. But
no. Okay. Let me stop.
When did we establish the concept of confidence interval?
No, we did not. So I have to track back my statement. What I said is wrong. So erase that from your memory. Okay. So if the sample value lies outside 2 times the standard error, then you reject. If it lies within, then do not reject.
Okay, so within 2 standard deviations,
yes.
Keep the hypothesis, but if it's outside of or greater than 2 standard deviations away,
you reject.
Or outside of the confidence interval, then you reject it. Okay, yes. Thank you.
Okay, yeah, we are not going to call this confidence interval. Okay, confidence interval is a slightly different concept. Okay, I'm not going to touch upon confidence interval because that's going to take another 15-20 minutes. Okay.
So, Professor, is this 68 and 95% are established truths kind of a thing?
Yes.
As far as okay.
Yes, that's if you can. This is a crazy thing. Okay, if you can do the mathematics, doing the mathematics, I don't say it's going to be easy. Normal distribution has very easily understandable properties, but doing the mathematics could be very difficult. But people have solved that within 1 standard deviation from the mean, we get about 68%. between 2 standard deviations about 95.4 or something, and 3 standard deviations about 99.9%. Okay, that's what we get. Now, okay, I think so here is a situation where sample mean M2 will be rejected. So when we have sample mean M2, then the hypothesis will be rejected. If our sample mean is M1, in this situation, the hypothesis will not be rejected. Okay. So that's what it is. So as you say, then p-value, what is this p-value? P-value, I mentioned earlier, right? You are going to look at this something called p-value. So let me go back here and tell you what p-value is. Okay, p-value is the area, this is the probability outside of the sample value. Okay, so we usually say, let us say our hypothesized population mean is 100 grams, and our calculated determined, no, our sample, actual measured sample mean is 112 grams. That's here. Okay, and then no, let's not do one. So okay, let's say our hypothesized population mean is 108 grams. Let us say 108. No, 102 grams. Let's say it's 102 grams. Okay, and the sample measured value is 112 grams. Okay, so what we want to do is in this distribution, we want to calculate the probability that the population mean, okay, or what is the area under the curve beyond the sample value, this entire area. Okay, this we calculate. Since this graph is symmetric, okay, this also means this area is also equal to this area. Okay, so we calculate this area and multiply that by 2, and we get what is called the p-value. Okay, now let us say this is our alpha. Okay, let me do these things here. Okay, this is my sample mean. Okay, and this is my alpha. Okay, this is my alpha. Okay, so if it is beyond this value, we have 2.5% here and 2.5% here. If my sample is before this threshold, before this boundary, you see the area under the curve is bigger than 2.5. Okay, that is, the probability is greater than alpha. Probability is greater than alpha. I should not, alpha is the value, so I should put threshold here. Okay, probability is greater than alpha. Okay, but if this were to be outside, let us say, where is this? Yeah, if it is this side, you see this is my threshold. Okay, this is the total area, and here is my sample mean. This is the area. The area outside the sample mean is less than the area outside the threshold. Therefore, P is less than threshold. If P is less than threshold, then you reject. Okay, if P is greater than the threshold, then you do not reject. Okay, that's where this comes from. Okay, so what is the take-home message? The take-home message is that we do not calculate census values. We very, very rarely do we calculate census values. We only do samples and we only get statistic. Once we get the statistic, we make a hypothesis on the parameter. And then what we do is use central limit theorem. And from the central limit theorem, you make a hypothesis on the parameter and see how far away from the sample is your parameter, is your hypothesis parameter. If it is far away, what is meant by far away? Far away is defined by that alpha. Alpha is for the probability. Therefore, the p-value that we calculate for the sample using the hypothesized population mean, if that p-value is less than alpha, then you reject the null hypothesis. Then you reject the hypothesis. Otherwise, you do not reject the hypothesis. So this is the message. I'm going to introduce a couple of terminologies. Okay, what is it? One is the hypothesis that we talked about. We always say, in fact, I blurted it out now. We say something called the null hypothesis. Okay? What is a null hypothesis? Null hypothesis is that the parameter value that we want to hypothesize is 0. Okay, so what does it mean? Let's say the weight of the 200,000 apples, the mean weight of the 200,000 apples I want to hypothesize is 120 grams. But how can it be 0? So what I do is, instead of writing mu is equal to 120, I write mu minus 120 is equal to 0. Okay, so that is the hypothesis I work with. Yes, Mohammed Niaz, go ahead.
Professor, the null hypothesis definition should be population mean minus m, right? Not mu.
Population mean mu is the hypothesized mean. Okay, so population mean minus hypothesized.
So what we are trying to say is the null hypothesis is the population mean and sample mean are converging, right?
No, null hypothesis is different. We just make some hypothesis for the population mean.
Okay. Fine. It is some unknown value.
It's some unknown value. Yeah. We do not know that, so we are hypothesizing a value for it.
Fine.
And okay. So instead of writing population mean is equal to the hypothesized value, we usually write population mean minus hypothesized value is 0.
Got it.
Yeah, I am hypothesizing 120. Whatever will be the population mean, that population mean minus 120 is 0. That's like saying my population mean is hypothesized value.
Yeah, absolutely. It means that the hypothesis is correct.
That's the hypothesis. See, this statement.
Yeah.
This statement is what we call as a hypothesis. Okay, and we actually call it the null hypothesis because we are always going to say the statement as the hypothesis, the mean minus hypothesized value is 0. Or sometimes we can say hypothesized value itself is 0.
Got it.
Sometimes you can say the hypothesized value itself is 0. So essentially what we are saying is population mean, whatever it is, I do not know, minus I am proposing a value. That value. So population mean minus my proposed value is 0. That means this is the value I am hypothesizing for the population.
Got it. Okay? Thanks.
This statement, it's a kind of a ridiculous statement. Why can't we just say the population value is this much? We can definitely say that. But what happens is, this hypothesis testing works on what is called the standard normal distribution. The distribution curve I showed you yesterday, that is called the standard normal distribution. Why? Because the value is centered around 0 and the standard deviation is equal to 1. So we always want to set the hypothesis to be the mean value to be 0. So it's based upon the standard normal distribution. Therefore, we want to get it this way. We want to state the hypothesis in this format. And since the whatever result left side is equal to 0, so it's the right side is 0. Since the right side is 0, this hypothesis is always called a null hypothesis.
So the hypothesized value is the is still the what do you call the hypothesis value of the mean population, right?
The mean population mean, yes, correct.
Which we will validate it through the samples.
Yes, exactly.
Okay.
Which
All
validate
right.
through samples, correct.
Yeah.
Sometimes this is hypothesized. Sometimes that is a constraint you might have. Okay, for example, like the bolt or nut example I gave you, the requirement is it has to be 8 mm. Okay, so that's a given. You have to manufacture it for 8 mm. So what do? You get a sample, make some measurement, and now compare it. You fix the population, the distribution of sample means is centered around 8 mm, and then you see how far away your sample mean is. The sample mean is far away from this 8 mm, far away with relation to standard error. No, it's greater than 2 standard errors. Then you discard your hypothesis. What is the hypothesis? The batch has a value different from 8 mm. The mean value different from 8 mm. Therefore, you discard the batch. Unfortunately, that's what you have to do. Okay. Otherwise, you don't discard. Okay. We always pitch the null hypothesis against an alternate hypothesis. It is usually denoted by the symbol H sub A. Some people write H sub 1, okay, numeral 1. You know, this is one very funny. The alternate hypothesis is that mean minus hypothesis value is not 0. Okay, it's not 0. It's different from 0. That's all. That's what we say. Now, this brings a philosophical question. Okay, when the p-value is less than 0, when the p-value is less than alpha, then we reject the null hypothesis. No, the hypothesis value we reject. When the p-value is not less than alpha, is equal to alpha or greater than alpha, if that is the case, all we can say is we do not reject the null hypothesis. We cannot say we accept the null hypothesis. Okay, that's a very subtle issue. Let me say why. Okay, here is my threshold. Okay, here is my population mean. My population mean is within 2 standard deviations, 2 standard errors. So I am not rejecting this hypothesis. That doesn't mean, no, I could have another sample mean, which is like here. With this also, I will not reject the hypothesis. Right? Or my sample mean could be somewhere here. With this also, I do not reject the hypothesis mean, this hypothesized mean. Okay? All I know is this cannot be rejected. This cannot be rejected. But that doesn't mean this is the population mean. Okay? There's another way of looking at it. Let me undo. Okay. Delete this.
Sir, what is the purpose of even stating the null and the alternative? Because as long as you'll keep trying getting closer to the population mean, always move away from that 95% to the 95 to 68 zone, increasing your trials with the samples.
You're dragging me deeper and deeper into problems here. The reason is there are 2 types of hypothesis testing. In this case, remember, we said it's symmetric, right? So even if it is on the right hand side, I'm going to consider the probability of this as well as the symmetric value this side. Okay, but in certain situations, we might have to look at only one side. Purely this, we would not consider this symmetric side on this side. Okay, when can we do that? For example, now in India at least, this drink called Complan, they advertise, your child grows 2 times taller. 2 times taller. Okay. So what does it mean? Grows. Okay, your child grows 2 times taller. Growth is, for children, the growth is always positive. They can only increase in height. No human has decreased in height, no, except in the very unfortunate and hopefully very, very rare situation where there are amputations. Right? Otherwise, people grow in height, except at very old age when the body fat shrinks. There may be a little bit of reduction in height, but otherwise people grow or saturate. Okay? So when you are looking at growth, right, the second measurement minus first measurement. Okay, measurement now minus height now minus height 3 months ago. That is going to be always positive or 0. So in that situation, the negative side will not make any sense. It will only the positive side will make sense. Therefore, the null hypothesis, what is the null hypothesis? The null hypothesis in certain situations can be the population mean minus hypothesis value is greater than 0. That is possible. Or less than 0. That's called one-sided test. That happens very, very rarely. To do one-side hypothesis testing, we have to be very, very theoretically strong, because people do one-sided hypothesis testing, and then theoretically it breaks down. So I don't even touch up on that in these classes, because most often we will never reach that situation. It happens very rarely. One tangible example I could give you was growth in height of people. There are only very few things like that. So since there are 2 types of alternate hypothesis possible, we have to state that.
Got it. Thank you.
Okay, so that's the reason why we have this. Otherwise, just this one statement is sufficient. Okay. Now I have about 5 minutes, so let me cover what is meant by confidence interval. Okay, let me cover what is meant by confidence interval. Okay, confidence interval is slightly different from this thing. Let me duplicate this slide. Okay, I'm going to say, please bear with me. And okay, this is going to be sample mean. Okay, my sample mean. I'm going to draw my distribution of sample means centered not around the hypothesized population mean, but centered around the sample mean. Okay, centered around the sample mean. Now this makes it a very different scenario, right? So what does it mean? Now this is the sample mean, okay, centered around the sample mean. Okay. Now, if my population mean is somewhere here, right? If my population mean is somewhere here, let me also change the color here so that it's all okay. If my population mean is somewhere here, then my population mean lies within two standard errors from the sample mean. Within this region, my population mean lies, right? Or I am hypothesizing that I do not know what this value is. I'm not even hypothesizing what the population mean is. When I talk about confidence interval, okay, when I talk about confidence interval, I am saying that this region, this boundary, some value here and some value here. This is the region within which I will be able to find the population mean with a probability of 95%. So that's a very abstract statement. I do not know whether you get the full gist of what I'm saying. Okay, I have the sample mean. I have found this. This is 2 standard errors away to the left, 2 standard errors away to the right, and within this interval, I have a 95% probability of finding the population mean. This is a very crude statement. Even this is a crude statement. Okay. So how would you calculate, how would you interpret 95% here? That means you will have to do lots of sample means. Every time you do the sample mean, every time you do a sample, you get a different sample mean. So you would draw different distribution like this. Okay, the one time I got this, one time this could be slightly different. One time this could be slightly different, so on and so forth. Okay, but whatever it is, 95% of those will contain the population mean within this particular interval. That's what it means, confidence interval. This again very confusing. So how do we deal with confidence interval? What we deal with confidence interval is that, remember what is the null hypothesis? The null hypothesis is population mean is equal to 0, or population mean minus that value is equal to 0. Right? Population mean minus that hypothesis value is equal to 0. Now, if this interval contains 0, then you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. This is the interpretation of confidence interval. Okay, so to me, many statisticians prefer confidence interval, but very heuristic understanding, very easy interpretation is given by the p-value, but the p-value has few other dangerous misinterpretations. I'm not going to go into all the theoretical and philosophical meaning of it, but essentially what you want to do is, if the p-value is greater than alpha, do not reject the null hypothesis. If it is less than alpha, reject the hypothesis. That's a take-home empirical statement. Second statement, if you find the confidence interval, if the confidence interval contains 0, okay, then your hypothesis mean is 0. Otherwise, it's different from 0. Null hypothesis is 0, right? 0, right? It's different from 0. So that's the take-home message from confidence interval. with this, I'll stop here. So we have come to the closure on statistical hypothesis testing. Yesterday, somebody mentioned about t-statistic. We will talk about t-statistic when we come to regression, which we will start on the next session. Okay, so I'll stop here. Of course, the initial part of the class was very easy to follow, but as we moved along, ideas, I mean, we know all the quantities, but how we put them together, that's where the challenges. I'm going to stop here. If you have any questions, please. Yes, Mohammed Niaz, please.
Professor, today a lot of good concepts, and it connected many core concepts of statistics and probability, and the pace of it teaching is also very good. And I understand that you feel you are going slow with respect to the curriculum. So my request, at least, if you want to have some additional sessions in between, please feel free to do that instead of keeping it at the end, like it could be in the mid. So, this is my suggestion. I don't know how far I would have, I would like to hear the cohort fellow students' perspectives also. I just wanted to convey my request here.
Thank you for that. Let's think about that. I need some consensus among the group. I'll also talk to the upgrade and GGU team whether something could be worked out.
Sure.
Yes, Chandrasekhar, please.
Sir, two questions, sir. So one is, based on last session and this session, the complexity is going up, right? So any suggestion from you on how we can kind of spend time in coming more prepared into these classes going forward? Otherwise, following may be difficult, is what I feel.
Well, pardon me for a lame attempt at a joke. Have a good night's sleep and come to this class with fresh mind. I do not, in fact, I can recommend quite a few books, but I don't want to do that because what I have covered in these 2 days are usually found in some 300 pages of books. They go into real details and give lots of examples that could actually overwhelm us. So we have tried to give you in a very concise capsule, in a capsule form, give you the essence of these things. So it's going to take a little bit of time to sink in. I understand that, but just be thinking about it. Don't worry about whether you understand fully well or not. Just keep thinking about it. Go through if needed, go through the videos a couple of times, go through the slide deck a couple of times, and things will start to make sense. Okay.
Sure.
At this stage, because this program is extremely fast-paced, I do not recommend traditional methods of learning. That will really actually demotivate you. My suggestion is just go with the flow, and things will become, you'll become more confident as you move along.
Got it, sir. And thank you, sir, for that. And the second question I had was, how is this course going to play out over the next couple of weeks? Because there are the Azure labs which are happening, the BI session that happened. So how is this going to converge, and how is it going to play out eventually?
Okay, BI session. In the BI session, probably you should have covered. The BI session should actually have happened after this particular session. Okay, that's my thing. Because in the BI session, you should have learned how to do all these simple statistics. Okay. Unfortunately, it happened earlier. That's okay. Now, the Azure, or in North America, they say Azure. In Asia, I think we call it Azure. Whatever it is, that is going to teach you how to do simple machine learning algorithms by drag and drop. And that Azure lab will make sense after the next session that we are going to do, the linear regression. Okay, and then maybe even logistic regression. That's when the Azure session will make sense. So the Azure session is going to help you understand machine learning. From next week onwards, we are jumping into supervised learning. Predicting a value. We talked about that in the first 2 sessions, right? We are going to start doing that from next session onwards.
Got it, sir. Thank you very much.
John Sirani and then Badr.
Okay. First of all, Rajan, very big thanks. First of all, yesterday's session I could easily follow because I done some homework. Today's session also in the first half, yes, I could. But as you already mentioned, it's the level of your complexities keep increasing. But I completely agree. I do not also want to go through 300 pages of books. But what I would still prefer, if possible, give some real world examples like how I'm going to use this for my thesis, or maybe where can I apply in my day to day. For example, if I'm building my app or something like this, I can relate offline after this class. But if possible, you can also give this examples, tiny. That could be also nicer. Yeah.
I will give you right away. I don't think you are going to use central limit theorem in any direct form at all in your life.
Okay. Thank you.
What you are going to do is you are going to use this one piece of information I told you, right? P-value greater than alpha, do not reject. P-value less than or equal to alpha, reject. Okay, that's the only thing you are going to use from now on.
Understood.
And to arrive at this inference, we spent all these things about central limit theorem. So if you want, you can, for all practical purposes, you can completely forget everything. Just remember these 2 nuggets of information.
Understood. Thank you, Rajan. Maybe one more small request. Is it possible, can we get the presentation of the next week now itself? Then I could do some preparations because it is
I will try. I'll try
yeah.
to post it in the in the portal.
Yeah, that would be very nice because this is what I could survive this week, first of all. Otherwise, I would not even. So that's why I'm asking as a kind help.
Sure.
If you would have given, it would be very, very, yeah.
I'll try to do that.
Yeah.
Sure.
Thank you. Thank you, Rajan.
Badr?
Yes, Rajan, thank you very much. It's a question about the assignment. We received the assignment on the Prism, but still we have some clarifications maybe or something like that. And also there is a data sheet, but it's not downloadable. We cannot download it. It's a CSV file, but we cannot download it.
Which one?
It's a CSV file for the first assignment.
Okay, that but you are not able to download?
We are not able to download it.
Huh.
Yeah. Can I share my screen? Let me share my screen.
It's logged as of now.
Yeah.
Perhaps like it may get opened up only before 2 weeks or something of that sort. I'm not sure.
Let me do one thing. Let me stop my, I don't know why I'm still sharing my screen. Now you can go ahead and share your screen.
Yeah, okay. Okay, so this is, can you see the screen?
Yes, I can.
Yeah, okay. So this is the first assignment. Okay, so there is something like a file to be downloaded here, but but I'm not able to download. I think even I asked some guys also, they cannot. They are not able
to link to this.
Yes, Rajan, that link is below and it is shown as logged. Badr, can you go back to the one step back?
Previous.
Yeah.
Okay.
And down, you can just the drop down. You click extend due date.
On the down arrow.
Just above that. Yes, exactly.
Mm-hmm.
So down, Rajan, you can see the right side. It is logged, right? So that's
it is logged. So what it means is this will not be opened until the opening date. So they will open it, I think, 1 week or 2 weeks before the due date.
Okay.
Okay, only then this will be unlocked. That time you will be able to see.
Got it. Got it. Thank you very
Okay,
much.
sure. Okay. Okay, everyone. Thank you. You all have a great week. If you still have the weekend left, enjoy your weekend. And for people on the eastern side of India, I'm sorry I took extra time today. Sorry. Take care. Bye bye.
Thank you.
Thank you, sir.
Thank you.
Thank you. Thank you all.
Thank you.
Thank you.